Topic of this talk is thermomechanical modelling on the evolution of magma reservoirs, and this is the work of Martin Letourneau. And I'd also like to acknowledge our co-authors on this study as well, John O'Sullivan, Darren Gravely, and Gil, who have helped us develop the models that I'm going to present. And really, look, the question we're trying to answer here is, when we're thinking about these magma reservoirs and how they're evolving over time, what is the effect of geometry? Does it make a difference as whether or not we assume it's a spherical magma chamber or something maybe more sill-like, an ellipse or a squashed cylinder? So magma reservoirs, at least from a modeling perspective, if we're trying to look at how they change over time, there are a number of processes we need to look in on and consider. So supposing I have this magma reservoir that exists at depth, we're going to imagine that it creates around itself some sort of superheated shell, a thermal aureole, where viscoelastic dissipation is dominant. And then above it, there may be some sort of brittle crust that hosts the entire unit. Now, this magma chamber will contain some volatiles. And one of the processes we need to think about is the dissolution or exsolution. So these volatiles coming in and out of solution in the melt component. At the same time, we may have some crystallization going on or some remelting. So we're going to need to think about changing amounts of crystals as a fraction. The volume and the pressure will evolve in this chamber over time, so it may grow and inflate, or it may contract depending on its temperature, pressure, and mass content. As it grows, it may induce pressures outside of itself in the viscoelastic shell, and those may be relaxed over time. And we're sort of thinking about those. If, however, they're not strong enough, then we may generate enough overpressure to propagate an eruption, and we're conceptualizing that as a dike that moves upwards to the surface. We also need to think about recharge of magma into this reservoir over time, either sporadic or some sort of average rate. The reservoir will cool over time by heat conduction through that viscoelastic shell. And finally, we'll allow that some sort of leakage of volatiles can occur across the shell. And they may be captured in the overlying brittle crust by hydrothermal systems that are circulating groundwater up there. And at least in the case of New Zealand, where these models are informed, that hydrothermal circulation may be recharged by groundwater, by rainfall. So there you go, that's the superposition of all of those processes together, and honestly it would take hours to discuss them all in the depth that they deserve. So let me just say that we have implemented all of them as discussed in previous presentations, and what we're looking at now is some of the effects of those models. So we are using in particular in a departure to De Kruijter and Huber and Mittal, who are the inspirations for this project. We're using a realistic magma petrology that we've derived from rhyolite melts. And so we have things like temperature and densities and volume fractions, which are all functions of our thermodynamic variables, in this case, pressure, specific enthalpy, and water content. And what these allow us to do is basically model from a 0D perspective eruptions from a magma reservoir. And here's how one of those reservoirs might look like over time. In black, you can see oscillations in the pressure increasing and then dropping, increasing and dropping as eruptions are occurring. Those are occurring because the magma reservoir has cooled down over time. It's hit some sort of isothermal region in which a lot of second boiling is occurring. And it's the pressurization from that that's driving those eruptions. And you can see here we're getting some kind of cumulative eruption volume over time. As the amount of melt trends downwards, that's being matched by essentially a solid fraction that's increasing over time. So this is just a general look at what we might get out of a model like this. Basically a bunch of time series to tell us how the system is evolving or what its trajectory is. So I guess one of the big things we looked at tackling with this project is the issue of magma reservoir geometry, because it's convenient in a lot of these models to assume that the magma chamber is spherical. You need to make some assumptions, of course, about the geometries, but we know in reality that they are not spherical. So for example, here's one sort of conceptual model of the development of plutons over time, and you can see they could have an extent that's very much longer, or rather vertically more extensive than they are horizontal. Or there's plenty of evidence, of course, as well for sill emplacements in various styles. So now you have a horizontal extent that's much larger than your vertical. So we know that the sphere is just one amongst many possible geometries, and we'd like to look at a general description of those other geometries. In New Zealand as well, we know that the caldera dimensions in the topovolcanic zone, where we have very large silicic eruptions, or have had in the past, we know that the dimensions of those are not consistent with spheres. So for example, here the Rotorua caldera has erupted 150 cubic kilometers in one eruption. And if you look at that, the equivalent sphere corresponding to that volume would only have a radius of 3.3 kilometers. That's much smaller than the caldera itself. Something similar further south here in Ohakuri, where there was an eruption of 100 cubic kilometers. There, the equivalent sphere is only just under 3 kilometers. Much more consistent with the caldera size, but still smaller. If instead you just sort of increase the size of that sphere so that it did match the footprint of the caldera, you're instead now looking at something that's much larger than the eruptive volume that's observed. So here, a 10-kilometer radius that does fill the caldera would produce 4,000 cubic kilometers of eruptive product, much larger than what has been documented. So the solution, of course, is to move to something that is non-spherical. And we have a couple of options for those geometries. One is just a squashed cylinder that I'm showing you here. It has some kind of upper surface area, some sort of thickness. And we can take the ratio of, if you like, the diameter to the thickness to get an aspect ratio, which is just one number that sort of characterizes that squashedness of the cylinder. Ellipses work just as well. Then in that case, things resolve quite nicely. In this case, the Mamaku ignimbrite that was erupted from this caldera can be described with something that has a radius of 10 kilometers, a thickness of 0.5 kilometer, and an aspect ratio of 40. Down here from the Ohakuri caldera, we're talking about something maybe a bit closer to an aspect ratio of 4. So how does geometry affect eruptive behavior? Well, there are a few changes we need to make in our simulation. For a start, we know that as reservoirs become non-spherical, they become more compressible. So if we take a sphere and we apply a pressure perturbation to it, if this is our magma reservoir, you'll see some sort of volume change in it. And the amount of volume you change you'll see is inversely proportional to a property called the compressibility. With an elliptical magma chamber, which is close enough to a squashed ellipse or a squashed cylinder, you actually see a much larger volume change for a given pressure perturbation. And in fact, the increase in volume will now be proportional to the aspect ratio, in addition to being inversely proportional to the compressibility. So that's what I mean when I say that they are more compressible. We see more volume change for a given pressure change. We also think, although we're less certain on this, that they are probably less viscously dissipated. So an important component in these models is the ability at which they relax overpressure and relax stress through viscous creep in the thermal aureole. And there have been some recent nice studies looking at relaxation in that aureole for different geometries. So for example, showing a study from Carenti here from a couple of years ago, looking as aspect ratio gets large, in this case theirs is the inverse of aspect ratio, they're seeing an increase in the Maxwell time. So that relaxation is taking longer, it's less effective. There was another earlier study looking at elliptical inclusions in viscous substrates. And this one as well suggested that there is perhaps some linear dependence on the effective viscosity on the aspect ratio. So these are pointing in the direction of maybe considering using an effective viscosity that scales with aspect ratio, and that's what we've decided to do here. I'd say that probably there's a good amount more work to be done looking at how this works in terms of proximity to the surface, different thicknesses of that shell, that kind of thing. We also think that with larger surface areas, you're likely to see an acceleration of both conductive cooling. So that's these little red squiggles. You can just fit more red squiggles for a larger surface area ellipse. And also volatile leakage. So the movement of volatiles across that shell into the overlying system. Again, you're going to have a greater opportunity to do that with a larger surface area. So we have implemented all these changes in our simulator, and then what we've done is basically just a large sweep of the parameter space to look at what the changes in eruptive behavior. So here I'm showing you simulations across a range of aspect ratios on the bottom there, looking from 1, which is a sphere, up until 1,000, which is very large, and then a range of volumes as well, cubic kilometers. We're only looking at models here where eruptions occurring by second boiling. So that's by cooling the system down to get that volatile dissolution. And in that case, what we see emerging is this idea of a Goldilocks zone. So that is a very precise combination of parameters for which eruptions can occur, and otherwise you just you're unable to produce the overpressurization required to trigger an eruption. We're seeing a lower limit on the aspect ratio. Below this limit, what we see is basically that cooling is not rapid enough to generate the overpressures that you need. You haven't got a large enough surface area on top of your magma reservoir. Whereas if the aspect ratio becomes too large, the reservoir itself becomes very compressible, and it's hard to build up overpressure in that sense. And so that's what gives us that Goldilocks zone there. We're also seeing that generally we can't generate eruptions in large reservoirs with some kind of upper cutoff of about 5 cubic kilometers, which was interesting as well. So let me just wrap it up. What we've been looking at is the effect of reservoir geometry on the triggering of eruptive behavior. We've been using these thermomechanical models that combine all these various processes. And we've essentially concluded that, for small magma reservoirs, yes, there is an effect of geometry for those eruptions that are triggered by second boiling. And moreover, there appears to be a very specific range in which you need that aspect ratio to lie before you have an eruptive system. So thank you very much for watching, and I hope to have a paper that we can share on this topic soon enough.